All right, as usual, let me give a couple of minutes for everybody to come on in, and then we'll get started. All right, let's get started for the day. So we're going to continue what we started last class, which is talking about circuits, basic DC circuits. And what we did last time was we introduced the theory, what to expect, how are things drawn, things like that. And so first thing to know is the big equation we're going to be using for this particular topic is Ohm's law. And Ohm's law is just an equation which shows the relationship between the three major quantities of interest for circuits, and that is the voltage, V, is equal to the current, I, times the resistance, R. Right, so V stands for voltage. And if you remember what voltage can be thought of, at least, you know, as a discussion for circuits, because voltage is something you get or is important in areas beyond just circuits, especially when you talk about electricity and magnetism, things like electromagnetic induction and all sorts of stuff. Voltage has certain meanings, but as it pertains to circuits, one usually finds it's a bit easier to get an intuitive view of what's going on when you relate it to something like maybe water flowing through pipes. So if you think of a circuit as a pipe system, and water will flow through these pipes, well, the voltage, which is usually the power source, so a battery or the outlets in a wall or whatever it might be, can be thought of as kind of like a pump. And this pump is what drives the current or drives the electricity flowing through the wire, just as a pump in piping helps to push the water through a pipe system where maybe the water wouldn't have gone normally. So the voltage is kind of like the pump pushing the current through the system. The units for voltage is capital V, and it's of course volts is the units. The next I stands for current. And the current is the flow of the electricity flowing through the wire. Of course, what we know nowadays is that the electricity flowing through a wire is the electrons in the wire, in the material of the wire, flowing through the wire or moving through the wire in some way. Of course, when it first started, Ben Franklin thought that the electricity, the current, was actually protons, because, of course, I guess the natural tendency is to think that it's the positive charge, which is the thing doing whatever it is it has to do. But it turned out to be the electrons. And so the current, just like with water and pipes, you know what water current is. It's the flow of the water going through. Well, same thing with electricity. The current is the flow of the electrons moving through your wire. And the unit for current is capital A, which stands for amps, AMP. Amperes is the full word, but we call it amps. And then the last variable, capital R, stands for the resistance of the circuit. And so with the pipe system, you can imagine maybe something like a constriction in your pipes. So you have a big wide open pipe, and then the pipe kind of reduces down to a smaller pipe in diameter. So there's a constriction there. Something is resisting the flow of the water from its natural state. And here in circuits, we call those resistors. And a resistor can be anything. More wires themselves, because as electrons trying to flow through the wire, well, there's a little bit of friction there. It's not perfectly easy for electrons to move around in the wire. And so the more wire you have, the more resistance there is. But then, of course, you could have more complex resistors. You know, a light bulb is a resistor, and a microwave can be thought of as a resistor. You know, anything you put into your circuit will inevitably increase the resistance of the circuit, because you're making it harder for the electrons to flow, because they have to go through whatever the thing is you just placed into your circuit. And the unit for resistance is the Greek letter omega, the capital omega, which looks kind of, you know, like a horseshoe. And it's called ohms, O-H-M, just like Ohm's law. Well, the resistance, the unit of resistance is called ohms. And that's our big equation, right? This is a relationship. It relates voltage, current, and resistance. And then we had a second equation, which was for power. The power of a circuit is given by the current multiplied by the voltage. So P is power. And its units is capital W for watts, W-A-T-T-S, watts. And so those are going to be the equations we want to use to calculate whatever it is our problems will ask us. We're going to be given circuits in some form, and we'll be asked something like, calculate the total current running through this circuit, or what's the power supplied by this circuit, or whatever the case may be. And then we discussed, or we showed how in practice people go about drawing or representing a circuit. Because of course, if you've ever seen a real life circuit, it's not that easy to draw. You have to, depending on what kind of circuit you're talking about, the actual small little electronic circuits versus the old school with big old resistors and stuff. Either way, you want to, of course, make it as simple as possible to show a circuit for someone to look at it and be able to recognize what's what, where is everything, what are all the pieces, without it taking you a long time to do. And so people created circuit diagrams. So these are like simple drawings which represent a true real life circuit. And so we showed that there are a couple of symbols you need to know. And the first, of course, is the voltage source. Looks like this. You have a little line and then a big line parallel to each other. And now that's drawn vertically. Of course, I could draw it horizontally too, depending on where it is in the circuit. This is the voltage source. And the other big symbol you need to know is the resistor, which looks like this jaggy, spiky wave looking thing. And depending if I draw it vertically or horizontally, that's what a resistor looks like. Okay. And then all you do is connect these symbols together in whatever way is necessary to represent the particular circuit you're talking about, using lines, and those lines represent the wire of the circuit, of course. And the current, there's no symbol for the current here. There is a simple symbol when you get deeper into circuits for a current source, but we're not going to need it for this particular semester, so I won't bother worrying about it. So basically, a nice simplified look for a circuit would be something like this, a circuit diagram, I should say. All right, here's a circuit diagram. We have some voltage source and some resistor, and it's connected with lines, and so this represents a circuit. Notice it's a closed loop. It starts at the voltage source, let's say, and then the wires move around. You have things plugged into it, in this case, a resistor, and the wires are all connected and they connect back to the starting point again. And of course, if we had this, then we can ask a question. We could say, what is the current which flows through this circuit? And so all you would do is you'd start with V equals IR. Solve this equation for I. So we get I is V over R. And then we'd plug in whatever the value of our voltage source is and the value of our resistor. All right, so that's what we did last time. Okay, are there any questions about the setup to what we're doing right now? Okay, so yeah, not really anything complicated yet. We're just, building our tools that we're going to be using. Now, at the end of the class last time, I talked about, well, there can be issues, of course, when we get more complicated circuits where maybe there's two resistors in my circuit. And the question is, if there's two resistors in my circuit, well, how do I go about calculating Ohm's law? Because Ohm's law only has one resistance in that equation, or at least a slot for one value of the resistance. So if I have two resistors, how do I plug both of those resistances into this one equation? Now, it seems like a stupid question. For instance, if I have a circuit that looks like this, here's one resistor, then the next resistor, and I say, okay, here's a voltage source, call this one R1 and call this one R2. And the question is, now what do I do for Ohm's law? Because there's only one R in my equation. So should I plug in R1? Should I plug in R2? Should I plug in the sum of the resistances? The difference in the resistances? Should I multiply the resistors together? Should I take the average? Well, this is a question. Give me 1 second really quick. Sorry about that. My alarm system started beeping. Anyway, the question is, how do I combine these resistors together so I can use Ohm's law for this type of circuit, a more complicated circuit, which is obviously what the vast majority of circuits we're going to be getting. We're never going to get as a question, here's a circuit with one voltage source and one resistor. Now answer these questions. That's boring. And like I said, this seems at first like kind of a stupid question. Obviously, if you have two resistors in your circuit, then you should add the resistances together. Because if you resist it by this much and then you resist it by that much afterwards, then the total resistance is like, well, you add the two resistances, which is a great thought. But however, we have to recall that there's a second way I drew this, and I'll draw it in a fancier way, which is this way right here. What if I draw my circuit like this? So now here's my V, here's my R1, here's my R2. It's a circuit, one voltage source, two resistors, just like the first one. However, now if we're careful about things and we try to use a little bit of intuition instead of just brute force naivety, we say, well, look, the first circuit, if I look at the current flows out of the voltage source, comes into R1, must go through R1, comes out, must go through R2, and then comes out and then continues along the circuit. Okay, so the current flows through both of these resistors. But then I look at the second circuit, and the current comes out of the voltage source, goes along, and then it hits this point right here. And at that point, all of a sudden, the path that this current can follow diverges. And there's two different paths I could send my current through. I could either have it continue along and have it hit R2 and then come out and continue along back to the beginning, or it could diverge downwards to R1 and go through R1 instead, and then continue along back to the beginning. Well, this is different, because if we think about the current as a bunch of electrons flowing through our circuit, which is what it is, then we can have a situation where some electrons are hitting R1 and some electrons are hitting R2, but obviously no electron will go through both R1 and R2. No electron feels the resistance, both resistances. They either feel one or they feel the other. So how in the world then Are we going to accommodate this? On the first circuit, every electron feels both resistors. So it seems logical that you should add the resistances. The second circuit, no electron feels both. Some will feel one and some will feel the other. So I would imagine, just purely by intuition, that these two things should be done differently. The answer for the first circuit is not going to be the same as the answer for the second. And so that's what we saw at the end of last class. And of course, today the plan is to actually solve this riddle. And the solution is, that's exactly right. My intuition is correct. These are two different circuits which act completely differently. And thus, we have to have a way of calculating the total resistance of a circuit based on how the resistors are connected. Because what the point is going to be in a second is to take a complicated circuit, choose either one of these, and either way, have it be represented by a new different circuit, which is like that very first example I showed. One single resistor sitting there, one voltage source, because that's what I could do Ohm's law with. So I have to find a way of taking some circuit, complicated, multiple resistors in it, simplify it, and represent it as this other circuit, which is a lot easier. So here's the thing. There's two ways that we're going to worry about of connecting resistors together. The first way is called series. If you connect two resistors in series, then that's something like this. Okay, you have two resistors, one's connected to the other, and what makes it series, one way of thinking about it, is every electron that hits the first resistor will also hit the second one. There's no choice. There's no divergent path here where the electron can hit the first one and then move and not hit the second one. If an electron comes in and hits R1, then it has to hit R2 as well. And thus they would be connected in series. The other way of connecting is parallel. And for parallel, one representation is something like this. Okay. So in this case, what you would have is, of course, current coming in. Then at this point, the paths diverge and some of the electrons will go to this guy and some of the electrons will go to this guy. And in this case, it's not like the series because any one of these electrons will either hit the top resistor or the bottom resistor, but there's no electron that is going to do both. If the electron went to the top path, then it's going to skip the bottom path. And of course, if it went to the bottom path, it skips the top. So for parallel, there will be some choice for the electron to make about which direction it'll flow. And it will only hit one or the other of the resistors. Okay, so that's the difference between series and parallel. Series, if the electron hits the first, it will inevitably hit the second. There's no choice. The electron has to go through both. Parallel, there is a choice. There's a path difference. And an electron can either hit one or it can hit the other, but it will never hit both. Okay, are there any questions about the difference between series and parallel? This is going to turn out to be the most critical part of what you do in circuit analysis. Because the rest is merely Ohm's law, V equals IR, that's it. That's not a big deal. The key to circuit analysis is looking at a circuit, looking at how the resistors are arranged, figuring out what's in series and what's in parallel, and then doing whatever simplification process we're about to learn to get it down to a single resistor type circuit. At that point, that's when we use Ohm's law. So being able to recognize if the resistors are in series or parallel is 95% of circuit analysis. And like I said, the best way of thinking about it, either the electrons must go through both, or they could either go through one or the other. Now, I think I also last time showed you the other way of doing it, which is the talk about nodes. And so if you want to do the node analysis way of figuring out if it's series and parallel, the rule goes like this. If you have a circuit, every element in your circuit, which means every voltage source, every resistor, you could put what's called a node, which is just like a little dot on each side of every element. So for this one, the first resistor has these two nodes. The second resistor has these two nodes. Okay, so that middle node there, both the first and the second resistor have that same node. They're connected to each other. However, their other nodes are not connected. The first resistor, his left node sitting there, is not touching the other resistor. It's its own thing. And the same goes for the right node of the second resistor. And so with series, the rule is they share one node in common. But then if we do parallel, the rule is same thing on either side of each resistor or voltage source or whatever in your circuit, you put a node. And so what we would have is a node here and here for that resistor and here for this resistor. And then we said, well, look, on the left side of these resistors, all of this stuff is just wire and there's nothing else there. So really, even though I drew it as two separate nodes, one on the top path, one on the bottom path, they're the same thing. It's just a piece of wire sitting there. And the same goes for the right side. Over here, these two nodes are really the same node. And so the rule for parallel, if you notice, the top resistor and the bottom resistor have the same two nodes. So if they share two nodes in common, they're in parallel. And so that's the other way of trying to analyze if it's series or parallel. If they only share one node in common, they're in series. And if they share two nodes in common, they're in parallel. So those are your two methods. Sometimes you use one method, sometimes you use the other. It just depends on the circuit you're looking at, what kind of makes sense to your mind as you think about these things. Now, let's say we're masters of being able to detect if this is series or parallel. What then? Once I've found out if the resistors are connected in series, how do I combine them? That's the point of what we're trying to do. And it turns out that for a series combination, the rule is that the total resistance of that series combination is given by the sum of the first resistor plus the second plus the third and so on. However many are connected in series, you just add those resistors up. So as an example, if we have something that looks like this, volts, let's say this is 2, this is 6, and this is 4. And I say, okay, let me look at this circuit. Let me see how the resistors are connected. Well, I look at the top branch here. The current's going to flow and it's going to hit the first resistor. Then it has to keep going, hits the second, then it keeps going and it hits the third. So there's no choices for these electrons. Every electron is going to go through all three of these guys. So all three of these are connected in series. Of course, I could also do the nodal analysis method, which is, hey, look, this first resistor has a node here and a node here. The second resistor has this node and this node. And the third resistor has this node and this node. Okay. And then I say, well, look, the first resistor and the second resistor share just this one node in common. And so the first and the second resistor must be in series. R1 and R2 are in series. But then R2 and R3 share this one node in common. And so I know R2 and R3 are in series. Well, if one is in series with two and two is in series with three, then all three of these guys are in series with each other. So either way I think about it, I find out that these three resistors are in series. Once I know that, then I say, okay, the total resistance of this particular circuit is R1 plus R2 plus R3, which is 2 plus 6 plus 4, which is 12. Okay, so this one's nice. The series connection is exactly what your logical intuition would tell you. If you have multiple resistors connected in a circuit, then the total resistance is just combining all the resistors together, adding them up. Any questions about this example? All right, well, that was the easy guy. The other one, parallel, this one's not quite as straightforward, unfortunately, but it's not bad. The rule is what it is. And a rule for parallel says this: 1 divided by the total resistance in parallel is equal to 1 divided by the first resistor plus 1 divided by the second resistor, and so on. So this particular equation is a little bit more complicated. If you have multiple resistors connected in parallel, to get the total resistance of that circuit, you take the inverse of the first resistor, so 1 over the first, plus 1 over the second, plus 1 over the third, and so on. You add all those 1 overs up, and you get a number. And whatever that number is, that's 1 divided by the total resistance. So you then flip the number upside down, and you get the true total resistance. That's the rule. Now let's see it in action. Here is our example. There's our circuit. And I say, okay, let's look to see, is this in series or parallel? And immediately I see it's parallel because at this point right here, the path diverges and some of the electrons will flow through the upper path and some will flow through the bottom path. So there's a choice for the electrons to make. No electron will feel both of these resistors. They will either feel the first or the second. So they're in parallel. Now that I know they're parallel, I say, well, 1 over the total resistance is 1 over the first resistor plus 1 over the second. So 1 over 3 plus 1 over 6, well, we have to remember how to add fractions. So if you've forgotten how to add fractions, remember the rule: you don't just add the numerators and add the denominators. You can't do that. To add fractions, you have to get a common denominator first, and then you can add the numerators. So for 3 and 6, the common denominator would be 6. So to make the first fraction, 1 over 3, have a 6 at the bottom, I multiply the top and bottom by 2. So this is the same as 2 over 6 plus 1 over 6. And then that's 3 over 6, which is 1/2. Okay. However, here's the key, and here's where lots of mistakes are made, especially on a test where you're timed and there's a deadline and you're rushing. 1/2 is not the answer. 1/2 is 1 over the answer. So I then have to flip this number to get the total resistance, which is actually 2. So don't forget this step. If you have parallel resistors, 1 over the first plus 1 over the second and so on gives you a number. That's not your answer. The answer is 1 over that number. So you have to remember to flip the answer at the end. But that's the rule. Okay, it's not as straightforward as the first. The first one's nice. You just add the resistors and you get a total resistance. That's series. Parallel, you add the inverses, the reciprocals. And then you take the reciprocal of that guy. Are there any questions about the parallel combination? All right, now I will warn you, if you look this up in a book or see people do it online or whatever, sometimes you might see something that looks like this. The total resistance in parallel is going to be, let's see, what would it be? How do they do it? I think it's, yeah, it was 9 over 18. I think it's R1 times R2 over R1 plus R2. I think that's what they usually have. Now, this is true, okay? All this is kind of a shortcut way of doing what this says to do, okay? It's just a little equation somebody made, which is a shortcut for adding the inverses. However, I'm going to warn you, even though this is correct, I never use this equation. The reason I never use it is because it only works if you're only talking about 2 resistors. So for instance, it works here. If we look, we say, okay, what's R1 is 3 times R2 is 6 divided by 3 plus 6. So it's 18 over 9, which is 2. Hey, that gives me the answer. Perfect. However, if instead what I had was this other circuit that looks like this, oops, with 3 resistors. Okay, 3, 6, 9. If that's what I have, I can't use that anymore. It's very tempting, and I used to see this both with some of my friends when we used to do homework together, and when I used to teach the electronics lab back at UNO. I would see people say, well, look, if that equation works, then, and if I have 3 resistors instead of just 2, all I do is R1 times R2 times R3 divided by R1 plus R2 plus R3. You know, I just generalize it. I add in the 3rd resistor. But that doesn't work. You can't do it with 3. At least you can't do it this easy. Once you have 3 resistors, you can't use the shortcut anymore, and you have to do the true actual equation. And because of this is just kind of my own philosophy of things. Since the shortcut doesn't work for everything, it only works for a very special case, I never use it. Because the danger is that either you or someone who's watching you will think you could use it in a time when you can't use it, and thus will get the problem incorrect because they tried using a shortcut that doesn't work for what they're doing. Secondly, because my memory is bad, I don't have a good memory. It's hard for me to memorize a lot of stuff. And back when I was a student, I had professors that forced you to memorize every equation. You didn't have formula sheets and stuff. I developed kind of a base foundation of all the equations I need. And all the other equations, which are nice and helpful, but I can get to using the original equations, I never memorized those. And so for me, since the first equation, the one I circled in red, can be used for every case, whereas the one I wrote in red, the shortcut guy, is only for certain cases, why would I learn both? Let me just learn the one that always works, and that's less I have to worry about filling up my mind with. So if you use the shortcut on a problem where it can be used, that's fine. I'm not going to take off or anything like that. But what I will say is my recommendation, just use the actual equation and work it out. That way, there's no chance of you trying to use the shortcut when you're not allowed to. It's not that much extra work. You're just adding fractions, and especially if you have a calculator, big deal. But I also wanted to show it to you in case you see it somewhere and you're like, what the heck is this? This is not the equation he showed us. Well, that's because I showed you the actual equation, not the shortcut. All right, so any questions about that? Well, let's try an example then. Here's an example. Circuit. $10 volts, 8 and 2. So here's a circuit, and I'd like to know what is the total resistance. So anybody know, are these two resistors connected in series or parallel? Any ideas? All right, well, I'll say they're in series. How do I know they're in series? Well, the first way is just thinking about the current as it flows through the circuit. As the current flows, it's going to hit this first resistor of 8, flow through it, and then it has to hit the second resistor of 2. So every electron is going to feel both of these resistors, thus they're in series with each other. So if they're in series, the total resistance in series is R1 plus R2, which is 8 plus 2, or 10 ohms. Okay. The other way of figuring it out is you say, well, let's put the little nodes on. So this resistor has these two. The second resistor has these two. And these two resistors share just this node in common. They share one node in common. That means they're in series. Okay. Another example. For this circuit, are these two resistors in series or parallel?
Parallel?
Parallel, okay. Anybody else want to guess? Do you agree? Do you disagree? Surely not everybody's still sleeping. Apparently everybody is. Well, let's look. What happens to the current? Current leaves the voltage source, hits the first resistor, goes through, keeps going, and then has to hit the second resistor. So again, what we have is a situation where the electrons have to go through both resistors. If they have to go through both, then they must be connected in series. And that's what's nice about this. It's easy for me to trick people. It's very tempting to say this is parallel. First of all, because it's drawn so that the resistors look like they're parallel to each other. But if you think about the difference between these two circuits, all I did here was, grab onto this first resistor and pull it over, stretching the wire a little bit so it's placed over here instead. I didn't take it out of the circuit, I just literally stretched the wire over. And so these two circuits are really the same thing. I mean, they have different numbers, but that's immaterial. To the electron's just flowing through. And remember, the thing about circuit diagrams is it's not literally what you see on a circuit, okay? It's just a representation, it's symbolic. And so if you have a true circuit sitting somewhere, that true circuit may look some weird thing where you have a battery and wires, and then over here you have the resistor plugged in to the circuit board, and then you have another wire over here, and then here you have another resistor plugged in, and then the wire. That may be what the circuit actually looks like, but of course that's messy. And so what a person would do is they redraw it using the circuit diagram symbology. And I could draw this circuit like that. I could draw it like that. I could draw it like this. These are all the same circuit. But I just have freedom about how I want to symbolically show it. As long as the connections are the same, then I can draw any one of these three circuits to represent that one over there, the actual physical circuit. Okay, now, how about this example? Now this guy, this is the parallel one. Now, why is that different than that one? Well, the reason, of course, is because you have this split sitting here. Okay, there's a split, and the electrons have to choose a path. There's no way for the electron to go through both paths unless we start getting into quantum mechanics. But in terms of just classical views of physics, it'll either go that way or it'll go that way. And since the electron will not go through both, but either one of them, I know it's parallel. And if it's parallel, of course, let's say this was 3 and 6. I've already done this example, but 1 over r is 1 over 3 plus 1 over 6, which gives rise to an answer of 2. Now, those were all the simplified examples. Let's take one a little more interesting. Let's say I have this circuit now. Okay. Now I have something interesting. If I were to say, are these three resistors connected in series or in parallel? You can't give me a real answer. It's neither. It's a combination of the two. We can see quite clearly that 2 and 4, they're connected in series, right? So if we forget about everything and we only zoom in to this part right here, and I redraw it over here, okay, and forget about everything else, then obviously when the current comes in, it hits the first guy and then it has to hit the second guy. So for these two resistors, that's series. However, zooming out, we see, well, wait, right here, there's a path difference. There's a divergence where the electrons can either go this way or they can go that way. What I know is that if they go the bottom way, then it's going to hit a series connection. And if it goes the top way, it just hits that one resistor. So there must be a parallel aspect to this in some way, right? There's a path change or there's a choice where it can either go to the top path or the bottom path. That's a clear sign of parallel. And if it goes to the bottom path, there's stuff in there that's series. So what do I do? And here's where all of the complication, all of the artistic creativity of doing circuit analysis comes in, okay? The problem with what I'm about to do is that I can't say, this is how you do it. This is the one way of doing it. This is how you think, and that's that. Because if I get 10 electrical engineers to solve the problem, I'll get 3 or 4 different ways of thinking about it. How do I want to do this? How do I think about it? Which order do I work on things? There's not one right way of doing things and one wrong way of doing things. Now, I'll show you what I would do. What I would do is I'd say, okay, I know that eventually what I want to do is simplify this circuit down. And so we're going to make use of this kind of tool, which is, what's it called? Forget the word, but it's basically, it's equivalent. I'm going to create an equivalent circuit. And an equivalent circuit just means it's a different circuit. However, it acts just like this guy does. If I plug it in and I put little measurement tools on it, the answers I would get from the equivalent circuit would be the same answers I would get from this guy. But the equivalent circuit is easier. And so if I do my calculations on the equivalent circuit, which is easier, that's a lot better. I'll get an answer, and I know the answer will be the same answer as it was for the complicated guy that I don't want to work on. So what I'm going to do is I'm going to say, look, I want to take this circuit and make it look like this. Okay, this is easier. This top path is the same. I haven't messed with that, but the bottom path I'm changing. Right now, this blue circuit, this equivalent circuit, is easier because there's just 2 resistors, and those 2 guys are going to be in parallel. The top circuit is more complicated. I can't just do parallel sitting there. So the first step I would do is I would take the bottom path, which I already know is series connection, combine those resistors together in series to get some new equivalent resistance. So if I do that, the equivalent series here is 2 plus 4, which is 6. Okay. And now I'm going to pretend I have a new circuit. The top is still 3, but now the bottom, instead of having a 2 and a 4, I've combined them to the equivalent resistance of 6. Okay. It's a different circuit, obviously. I don't have 3 resistors anymore, I only have 2. However, if I calculate the current of this guy, it's the same as the current of the problem itself, the very first circuit I drew. All right, well, now what do? I say, look, I have a path split. Some electrons go that way, some electrons go this way. They're in parallel. So 1 over R parallel is 1 over 3 plus 1 over 6, which is 1/2. But that's 1 over R parallel, so I have to flip it, and I get R parallel then must be 2. What did I just do? I combine these two resistors. I know they're connected in parallel. I calculated what the equivalent total resistance is of the parallel connection. Turns out it's 2. And so now what I have is some new circuit with just one resistor. And that guy's resistance is this 2 I just calculated. And of course, the voltage source is still 10, just like before. And now what I've done is I've simplified my complicated circuit, which had 3 resistors in some combination of series and parallel, little by little, worked it down to an equivalent circuit, which is very simple. A single resistor with a voltage source. I could do Ohm's law and everything I want. And this is going to be the goal. This is going to be your job. Okay. Take the complicated circuit I give you. With that circuit, you figure out, are the resistors connected in series? Are they connected in parallel? Some will be in one way, some will be in both. It just depends. However, you look at what you can work on that little piece, you get an equivalent resistance. Redraw the circuit, or at least just think about it in your mind. And now you say, what's the next thing I could do? Well, now these guys are in this connection, so let me combine them together. And you go one step at a time, simplifying one time after one time until you get down to your final equivalent circuit. And then with that, that's when we use Ohm's law. That's when we use the power equation and so forth. Okay, so if the question was, here's a circuit, what's the total resistance of the circuit? Well, I look at it, I say, okay, this is a combination of stuff. It's not just parallel, it's not just series. So let me simplify it. First simplification I would make, combine the 2 and the 4 together. They're in series, so I combine them by series and I get a total resistance of 6. I now redraw the circuit where instead of having the 2 and the 4, I replace it with the equivalent that I just calculated, which is 6. And now I reanalyze it. I say, now what do I have? Now I have 2 resistors which are connected in parallel. All right, we'll combine them in parallel, get an answer. I get a total resistance of 2. Now I'm left with just one resistor whose resistance is 2. So the total resistance of the circuit must be 2. All right, any questions about this, this example?
Okay, it's not a question about this example, but I just did have a question. So like, for example, if you had, let's say example like this example in the black, but let's say there was a second resistor on the top, it would just be easier to just call it parallel and then combine the 2 together, or combine, I guess, like the top 2 together and then the bottom 2 together.
So what you'd like to find out about is this here.
Yeah, something like this, yes.
Okay. Yeah, so if I see this, first of all, your question is basically, number 1, should I either just combine them in parallel, because now you have the same thing on the top as the bottom, or should you combine series, and then combine those 2 things in parallel?
Yeah.
Okay, very good question. The second is the answer. And the reason is because if we tried to do straight up parallel, okay, if we tried to do 1 over R parallel is 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4, right? Oops, 1 over. So call this, 1, 2, 3, and 4. Let's say I tried it. What would this tell me? This is thinking what you have is that all 4 of the resistors are parallel to each other. Okay, and so what that would look like would be this.
Oh, okay. Yeah, that is different. Yeah, yeah, yeah.
And that is because if you notice, every electron is either going to hit the first resistor or the second or the third or the fourth. But there's no electron that'll hit, two of them or three of them. It can single, you just think about one electron. It's either going to hit one or two or three or four. That's what I wrote there and with the parallel implies. With your example, however, take an electron. If it takes the bottom path, well, he's going to hit 3 and 4. So it can't be that this one electron is only going to hit one resistor. If it goes through a path, it's going to be hitting 2 either way. It's either going to hit 1 and 2, or it's going to hit 3 and 4. And that kind of tells you, okay, what you have is a parallel piece for the 2 branches, but either one of these branches, there's series stuff in it. So what I would do is combine these in series, and you get some new resistance, and these in series, new resistance. And then that becomes what this looks like in blue.
Yeah.
It's a basic 2 resistors in parallel with each other. Yeah. So that's the thing. And that's kind of the mentality we have to get into to start to be good with this stuff, is what's kind of the intuitive feeling this is telling me. This means all 4 of these resistors are parallel to each other. None of them are connected to each other in series. And so, yeah, that's a very good question. And it does come up, because like I said, there's different ways of going about solving some of these things. And the question is always going to arise, should I do the series first or should I do the parallel first? And there's no perfect answer. Each answer will depend on the particular circuit as it's drawn, what's the best way of handling it. And for me, it's just kind of a feeling you get when you look at the problem. When I look at this first example with the 3 resistors sitting here, I say, okay, I know I have 2 branches which are parallel, but before that parallel thing, I've got one of the branches is already in series. So take care of the series first. Once I take care of the series, now all I'm left with is the parallel by itself, and that's what I want. What I've seen in the past, I see it every semester, is, let's take this example and I'll redraw it just so it's a little cleaner. I'll see this example. Call this R1, R2, R3. What I'll see is people will say, look, these 2 branches are in parallel. So why don't I just do 1 over R parallel is 1 over R1 plus 1 over R2 and get an answer. And then I'll have another R parallel, which is 1 over R1 plus 1 over R3. Because R1 is parallel to R2.
Oh,
R1
yeah. That makes sense.
And I have those 2 answers, and then I can add those 2 answers together. This doesn't work, because that's why sometimes it's nice to look at the nodes. If I look at the nodes, this bottom path has these nodes, so R2 and R3, and then R1 has these nodes, but I know these are the same and these are the same, right? And so if this were true, then it must be, remember the rule for parallel is the 2 resistors share 2 nodes in common. Well, look at R1 and R2. R1 and R2 share this left node, but R2's right node is not touched by R1. And the same for R1 and R3. R1 and R3 share this right node together.
The right node, but not the left node.
Not that left one. So R1 is not in parallel with 2, and it's not in parallel with 3. What it's in parallel with is the
combination of 2 and 3.
That's right? Exactly right. That's exactly right. Now, unfortunately, and this is why the nodal analysis is not always perfect, because someone always comes back and says, okay, well, you said our 2 resistors are in series if they share 1 node in common. Well, look, R1 and R2 share this 1 node in common. So aren't they in series? I'm like, oh God. Yeah, I mean, that's flawless logic. It's perfect logic. And that's kind of the weakness of the nodal thing. And the answer I try to give is they're not in series because, first of all, well, you have to use the logic of looking at the electrons, the current. An electron that goes to R1 cannot hit R2. And an electron that hits R2 cannot hit R1. So they can't be in series, because if they're in series, the electron has to go through both. Okay. So that's why I give both of these logical, or both of these ways of looking to see if it's series or parallel. The nodal way works a lot of the times. But when you get this question, which is kind of unique, well, it looks like R1 and R2 should be series since they share one node in common. But of course, we know it's not in series. And how I know? Well, I have to use the other method, which is the logical, follow the current, what's happening there. So for me, what I would say as advice is, given something like this, do the simplest things you can do first. And when I see this, this is the simplest thing sitting there. 2 resistors sitting there in series, add them together and replace it. And now look at what you have.
Okay,
And
it's
then
easy
go to the
parallel.
next simplest thing. Don't try to go with the most complicated, which is, how do I combine R1 and R2 together? Oh my God, that's way more complicated. Just do R2 and R3 and you're fine. Because from there, when you redraw it, the thing you redraw is simple too. It's just this little parallel guy. And I can do parallel, that's easy. So, there's good news and bad news. The good news is there's only 2 choices. They're either going to be in series or parallel, or there is a third choice. The third choice is they're in neither yet, but after you simplify it some, now it'll unlock that they're in series. Like, what I mean is, with this example, R1 is neither in series or parallel with any of them yet. But once I've simplified 2 and 3 together, now R1 is in parallel and I could start working on him. So that's the good news. The good news is it's either going to be series or parallel. The bad news is every circuit is different and there's no pure recipe for this is the order you want to do. Do this first, then you do that, then you do this. I can't say work the series stuff first, then do parallel after. Because sometimes you have to do the parallel. And here's a quick example. What about this guy? What if I have this?
Also, this time the branch isn't actually at the start, or the split isn't at the start. It's now
Right.
parallel. Okay, yeah.
And so this is tempting to say, look, this guy and this guy are in series, kind of like this. R2 and R3 look like they're in series. 1 and 2 kind of look like they're in series, but I can't.
Because of the node.
Right, because this guy is kind of messing with this 2. He's connected to them. So in other words, an electron that comes in and hits the first resistor will not necessarily hit the second resistor, because the electron may go up this way instead of hitting him. So I can't do the series yet, but I can do the parallel first. So work the parallel first, you get some equivalent resistance, and then when you redraw it, this guy's still 1, and now this thing is whatever the parallel was. And now you can see this is definitely series. So, like I said, I can't say always do series, then do parallel, which is what this needed, because here's an example where I had to do parallel first. What I can say is look at what looks the easiest or the simplest combinations first. Work those out, redraw it, and then see what's left over. And a lot of times what starts as very complicated looking will become very simple when you work those small pieces out first. Okay. All right, are there any other questions about what we've done so far? Now, this is definitely a topic that needs examples. Okay, next class, I'm going to work a bunch of examples on this. I'm going to post a bunch of practice problems and stuff for you to look at, but you have to practice problems too, because I promise you that, even if when you're looking at what I'm doing, you can follow it completely. It looks perfectly logical. I myself, years of experience with this stuff, I still get tricked up sometimes as I work some of these problems. Like, oh, I don't know, should I do this? And I'll, work one way and then find out, oh, I messed up and have to start it over again. You have to work a bunch of examples for this to become more and more comfortable to you, because there's just so many examples I could give you that are all different, that it's very likely on a test you could get a circuit you haven't seen yet. So the more examples you work, the more comfortable you'll be. And if you do get a circuit you haven't seen before, it won't be that big of a deal, because it'll be similar to something you've done before. So I'm going to post a bunch of practice problems on Canvas. When they're posted, definitely work them yourself. Take 30 minutes or an hour out of your day and just sit down and work them out. But next class, of course, I'll do more examples, and we'll go from there. The next step, of course, is once we've calculated the total resistance, let's use Ohm's law. Okay, and that's about as far as we're going to do with circuits. We're not going to get into the more complex methodology of what if you have a circuit where you can't do series or parallel, because those exist. There's a lot of those. So when you talk about circuit analysis, we go a lot further. We're going to stick to the fundamental thing, which is this. Given resistors connected, figure out if they're series or parallel, combine the resistors. And then once you've done that, do Ohm's law to get the current or get the voltage or whatever it is we want to get. All right, with that, you are free to go. Enjoy the rest of your day, and I will see you on the next class.
I had just one last question. So you were talking about like how when you're doing problems that you can like intuitively say, okay, this is not right, or like, is there like how exactly would you go about like, I guess, checking your work when doing a problem like this?
Yeah. For the types of circuits I'm going to be giving you, we're not going to really have places where that is too much of a worry. It's how can I put it? You won't come up to a point with these types of circuits where you're like, oh, okay, I know I must have done something wrong because now I'm stuck.
Oh, okay.
However, like I teach Physics 323, which is the circuit analysis class, which the whole semester is just circuits. And there, what we do is after we learn this Ohm's law stuff, then we learn things like mesh analysis, loop analysis, delta Y transformations, very fancy techniques.
Mm-hmm.
And with those techniques, you learn here's 7 methods for solving a circuit, but not all 7 work. And so you're going to be given a circuit that's complicated, and you just have to try different methods. And as you try a method, you may simplify your circuit down to a point where you can't do anything else. And if you get to that point, you say, aha, since I can't go any further, I must have used the wrong method. Let's go back to the beginning and try a different method. For these, since everything will be series or parallel, you're going to be able to complete it no matter what. The problem, which I think is your biggest concern, is, well, you can do it wrong and still get an answer, right? If I did what I was saying here and try to do like these, well, let me say R1 is parallel to R2 and R1 is parallel to R3. Well, I could do that and get an answer. It's just that the answer is wrong. So how do you know if the answer is right or wrong? I can't say there's definitely a way. What I can say is this: there are 2 rules about series and parallel. And I can write them up here with the series and parallel. The first rule is if you have resistors in series, The rule says the total resistance is always greater than any one of the resistors that are in series. Right? That's absolutely reasonable. If you have 2 plus 6 plus 4 and you get 12, well, 12 is going to be bigger than 6, it's going to be bigger than 4, and it's going to be bigger than 2. Right? The total resistance of the resistors in series is bigger than any one of the resistors in series. Obviously. Parallel is not so obvious. Parallel says the total resistance in parallel is always less than either one of the resistors. And we can see the answer right here. I have a circuit, and no one mentioned it, and I didn't mention it either, but it seems wrong. I have a circuit. One resistor is 6, the other resistor is 3, and somehow the total resistance of this circuit is less than those things. And so somehow you get really resistive objects, you put them in your circuit in some way, and the circuit is not that resistive. Somehow it lowers the resistance. And so that's another rule. So that's another thing you can look at as you're going through, and you say, well, I know these are connected in parallel, but my answer is bigger than this resistor. So I must have done my math wrong somewhere. Let me go back and check. There's things like that we can do. But what I can't say is, well, if you tried this example and you did it incorrectly, that you can look at the answer and tell that you did it incorrectly.
Yeah.
You can't do that, unfortunately. Because no matter what you try, you're going to be using an equation which relies on the fact that you're giving it good numbers. So in other words, I can't say, okay, well, just use Ohm's law, V equals IR, and then plug in the current you got, plug in your resistance, and see if this voltage matches that voltage.
What if the resistance is wrong? Yeah, so
Right.
that makes
Well,
sense.
Yeah, you calculated the current using the wrong resistance. So
Yeah.
obviously it's going to give you the right answer, even though it's wrong. So at least at this point, there's not really going to be a way of doing it. And that's why working examples over and over and over again is the key to this, because there's thousands of circuits I can give you, all of them slightly different from each other. And it's just a matter of getting used to, I can definitely tell if this is in series or this is in parallel. And the more you see, the better you're going to get at it. There's no like fallback where, well, no matter what, at the end of the day, I just do this little thing and it'll tell me if I was right. I wish that was true, but that's why they pay electrical engineers so much money, because they're good at this stuff and not everybody is. So
All right.
unfortunately, not a pleasing answer, but it's what I know. So
Well, thank you for that.
Yeah,
and then
yeah.
where can we find the practice problems again? It's gonna be on Canvas.
yeah, I'm going to post them on Canvas, just like always in the module section for this
Gotcha.
stuff. I'm going to write up the problems and the solutions and post it on there.
Okay, thank you very much. You have a good one, Mr. Rothman.
All right, you too.